Hi there, may I present to you an algorithm for dense semi-definite optimization. I underline the word dense because I don't dream ever be faster than solvers like Mosaic for sparse semi-definite programming. The software I present, the project I present, is not for sparse matrices. It's based on a cutting plane technology using an algorithm called projective cutting planes. Projective is not used in the sense orthogonal projection, but in the following sense. At the very first iteration, we have no information about the constraints of the feasible area, like in any cutting planes algorithm. And we can advance from some feasible solution towards the direction of the objective function. In this sense, it's a projection because it's a projection along a given direction, but not an orthogonal projection. The algorithm needs a starting feasible point, and I will give information on that later in the context of semi-definite optimization. So let's say I solve this projection problem, which consists of finding the intersection point between this direction and a facet of the feasible area. It's like shooting from a given point y1 towards the considered direction until the bullet hits the boundary of the feasible area somewhere on some feasible solution in red here, which is called y1 plus t1 star d1, which is a contact point, the place where the bullet hits the feasible area. And like in any cutting planes algorithm, at each iteration we maintain an outer approximation of the feasible area. At this point we only have one constraint, so the feasible area is this big triangle because we are in non-negative variables y here, and this may have an optimal solution depicted by the blue arrow at the right, opt p1, the optimal value over the first polytope p1. Then we take a point between y1 and the contact point, let's say in the blue square y2. We project again, but this time towards the best outer solution we have, opt p1. And by projection we find another facet of the polytope, the small blue disk, and another facet of the feasible area, which gives us a better outer approximation called p2. And the optimal value of P2, the optimal solution of P2 is it's depicted here if you follow my mouse. We will take a projection towards this point. This is what happened. We take in red this inner point y3 towards the best known outer solution opt P2. And by finding a new projection, let's imagine that at this moment we do find the feasible area of the original problem, the polytope P. So let's say I discovered all constraints, but the algorithm did not yet prove that the optimal value is opt P3, but it's enough to do another projection in green, and in this case T star, the step length, is 1, which means we cannot separate opt P3, and this means opt P3 is the feasible, the optimal solution over the given polytope P. Okay, this proves the optimality of P, and you can see that the proposed method is convergent. Why? At each iteration, like in a standard cutting planes algorithm, we cut one hour solution. We first cut opt P1, then we cut opt P3, then opt P2, then opt P3. Here these solutions are on a line because it's a simplification of the real world situation where unfortunately the outer solutions can jump from one area of the space to another in using, maybe even going into some bang effects, which are quite difficult to handle. But thanks to the inner solutions, the process is more stable than a classical cutting planes. And the main advantage of it is the fact that we generate along the way a trajectory of feasible points. So we can also stop the process when we think that the outer solution, which is an upper bound in an optimization problem, and the inner solution are close enough. This builds on existing work, and the fact that the convergence proof is so easy did not happen by happenstance. I may say that in my previous work I needed proofs of a few pages for this question, but the new method was designed to be more general and when possible as simple as possible and still effective. I first worked on this in a purely linear context, but this talk takes the proposed projective cutting planes to a higher level because we address a non-linear problem, which is semi-definite optimization. So let's consider this semi-definite optimization SDP problem. We have scalar variables from y1, y2 to yk. The C, A1, A2 and AK are symmetric matrices of size n times n. We optimize a linear function in variables y. And what is the main constraint in SDP problem is that this matrix is SDP. This can equivalently be written as follows. A matrix X is SDP if this product that is developed here is always non-negative for any v, any vector v of n components. So this is one of the main definition of an SDP matrix, which simulates or takes to a higher level the idea of positive numbers, because this is a kind of squaring operations if we want. If we reduce this to dimension 1, so for n equals 1, we basically say that some x is positive if and only if x multiplied by v1 square, if you want a v square, we have dimension 1, is always non-negative. Okay, so I will work with projective cutting planes on this SDP problem. Let me first work in more detail this SDP constraint that I already mentioned. It is written this way. In some sense, it describes the SDP cone as a polytope with infinitely many constraints, one for each vector v of n components. This is called the semi-infinite formulation of the SDP cone. Recall that in this context, X, as defined also in the previous slide, it's a linear combination defined by variables y from 1 to k, and we say that a solution y is feasible in the previous program if it respects this SDP constraint. So again, this happens if this is true, as it's a different way of writing the same constraint as in the previous slide. We can go back, so it's a rewriting of this stuff. Okay, so what happened? Classical algebraic manipulation makes these things equivalent. And now let us focus on the way I like to see this constraint written. It is written this way. So the eigenvector corresponding to the minimum eigenvalue of x gives the strongest constraint of this form for a given y. So let me go back to the SDP program and I rewrite it in this manner by writing the constraint the way I like it. I consider alongside the SDP constraint some linear constraints, like in a linear program, so that the variable y, they live at the same time in the cone defined by the SDP constraint, but they also live in a polytope. And using this formulation, you can easily see that we can solve this by classical cutting planes by separating iteration by iteration in feasible solution y out, which correspond at each iteration to the optimum value of an outer polytope that has, which is a program of the same form as this one, is only that instead of considering all possible v, it considers only a subset of V, because at each iteration, a cutting plane algorithm has a finite number of constraints to deal. This way of optimizing an SDP program is generally considered by most people I talked to not very effective, and the existing work on this idea remains a rare sight. I did try to find as much as possible, and there are a half dozen of articles on some particular cases of this program. But now I want to address this program using some, however, let's say a better technology, better cutting planes technology. So the cutting planes framework, let me just insist before going through the algorithm, it has some advantages. So imagine that the tight or saturated constraints that we generated at some iteration belongs to some set of vectors V. Let's name it veccuts now. And what happens at a given iteration, a cutting planes algorithm, either the standard one, either the projective one that I introduced here, will maintain a program of this form, okay, which has an optimal solution Y out. But for each V here, in the set of constraints known up to now, there is a dual variable which is non-negative, because I have a constraint of this form, and this dual solution, if I consider here only the saturated constraints that have a non-zero alpha V, will naturally satisfy this using LP duality. And if we work this a bit, this is equivalent to the following way of writing it. And here, if I name this sum of matrices, recall this is an n times matrix multiplied by a scalar, which is the dual value associated to the cut resulting from vector V. If I call this Z, you notice this is an SDP solution, because alpha V is positive, and this is a rank 1 matrix, which is SDP, which means that Z is a feasible solution in the dual SDP. If you write the dual SDP of the program I started with, you'll find it has to satisfy a constraint of this type. Here I ignored the LP part, because I simply imagined that at some iteration the LP part may not be needed may not be included in the tight or the saturated constraints at the given iteration. But it's not very complicated to integrate them and we obtain the same result. Projective cutting planes will still use the cutting planes framework, but it will generate at each iteration a primal feasible Y according to the black trajectory I presented when I first introduced projective cutting planes in the very first slides. But also it can produce at each iteration this kind of dual solution Z. So at each moment, at each iteration, it can give you a feasible primal solution and a dual feasible solution, something that, for instance, an IPM cannot do. It cannot provide this kind of things by default along the way, even if this may be questioned to, generally speaking, the standard IPM framework does not provide this, because it generates some solutions along the iteration so that X times Z, it's the identity multiplied by mu. They are not feasible. But if we have a heuristic, for instance, to turn a non-feasible Z into a feasible one, or a non-feasible Y into a feasible one, maybe things can be done, but I don't know more about it. But I do need an SDP heuristic in my algorithm, because, as I said in the very beginning, I need a feasible starting point just to start. I did not find an SDP heuristic published in the literature. If you know any, maybe I did not search enough, don't hesitate to give me some feedback. So I had to do it myself. I did find some trick quite simple. Let's say we have some Y which is not feasible. a non-feasible y, it's easy to find. We take a random one, or we take 0. If it's feasible, we are happy. If it's not feasible, let's see how we can turn it into a feasible y. If y is not feasible, this means that there is a v associated to the minimum eigenvalue lambda minus of x, such that this is negative. Okay, so x is not SDP, the definition. What happens? Let me introduce this function f, which is linear, so that f0 is lambda minus. What happens here? I take the same stuff as above, but I replace yi with some yi plus di. It's still a kind of projection starting from a solution y. I ask what happens if I go into some direction d, if I move from y to y plus d. How does the minimum eigenvalue function evolves? And what happens? If we maximize f over all direction d in a small hypercube, we measure the evolution of this function in a neighborhood in a hypercube around y. If the solution of this maximization problem is above lambda minus 1, strictly above, we can make a step from y towards y plus d and improve the minimum eigenvalue, which means we are going closer to the SDP cone. And why this has to work? Because, it may be problematic in terms of the number of steps needed to reach the feasible area. But why it's always possible to get closer to the feasible area? Because, well, let's say there is a feasible solution y. This means that if we replace here in this function d with y star minus y, we basically obtain the same formula as here, but with yi replaced by yi star. And if y star is feasible, this means that this value will have to be less than greater or equal to 0. So this means that the function f, if we advance from 0 towards this d, it will get higher and higher. Why is that? Because the minimum eigenvalue is concave. So if by advancing up to y star minus y, we improve the value of f, since it's convex, by advancing a very small step towards the same direction, it has to go up, the function, because otherwise, if it goes down, it will go down forever. A concave function that goes down when moving towards a given direction, if it goes down when advancing an infinitesimal step epsilon, it will go down forever. So this means there is surely an improving step d in the hypercube. Of course, this is the starting idea. Then we have to do multiple iterations. We need to check how long to advance along each d. Hopefully, for many instances, like the ones I will present next, it worked. Then, let me go back. I will present projective cutting planes. Let me go back to the program we have. And let's suppose we do have an inner feasible solution to start from. What is the main tool of the projective cutting planes? Is to upgrade the separation subproblem to a projection subproblem. Given some feasible y and an arbitrary direction, y out minus y for instance, what is the maximum step length so that we remain in the SDP area? Okay, so what happens in SDP programming? Projecting from y to d requires solving this problem. Here I imagine that the linear constraints, if any, are actually satisfied, if you want, by the outer solution, because the outer solution I use at each moment is obtained by optimizing a polytope, a linear program that integrates all given starting linear constraints and some constraints associated to some v here. So all considered y here do satisfy the given initial linear constraints. So the only question is how far we can go until getting to a contact point with the boundary of the SDP cone. I recall this is X, which has to be SDP when Y is feasible, but D, it has a form like that, it may be SDP or not. So basically we have to project from X towards D in the SDP cone. The problem reduces to this one, and this is the main building block of the algorithm. I do not have the time to get into all details of this because it takes more time maybe than everything else, but there is a written paper about it, or it will be available very soon. But the question is described here, and what happens. Let me first give you a very easy to implement approach if you ever just want to test this, for instance, very rapidly. What happens? The T star here will make the minimum eigenvalue of this function 0. Okay, so this means that if you work a bit the algebra, there is a vector v which will satisfy this. Okay, because it will be always on the boundary of the SDP cone. But if it satisfies this, v is actually a generalized eigenvector of x and minus d. So most software like MATLAB or Julia and maybe others do have functions that compute the generalized eigenvectors. So this could make the approach somehow easy to implement, but it will not be effective at all, because we need a very particular generalized eigenvalue, namely the lowest real eigenvalue above 0, because the algorithm for computing generalized eigenvalues are even more complicated than those for the simple eigenvalues. We can have complex values even, and x and d are symmetric. So with existing software I could not possibly use this approach to have a very effective algorithm, because to make the projective cutting planes work, you will see I have to be a bit obsessed by speed, otherwise it will not work. Because the main challenge is the speed of the projection algorithm to calculate this intersection, and it should be closer to computing a Cholesky or the smallest eigenvalue of the matrix. If the speed is closer to computing the whole eigen decomposition, everything is lost. Not to mention the whole generalized eigen decomposition. If we ask for all generalized eigenvalues and then check and then seek the one we are interested in, it is really much too slow. Let me discuss the projection problem more in detail and the solution method. So surprisingly, the subproblem is quite simple if X is strictly SDP. In this case, we have a unique Cholesky factorization, X equals KK transpose, and K is non-singular and triangular. So what we do next, we determine very fast by back substitution the solution D prime of this system. Since K is triangular, back substitution will work very rapidly in MATLAB. And why do I need this? Because the initial problem is this one. If I rewrite it using the Cholesky decomposition is this one. And now there is a property which makes these two problems equivalent, because we have something that is left multiplied by K and right multiplied by K transposed. So the SDP status of a matrix does not change if we left multiply it with an invertible matrix, and if we multiply it with the transposed of that matrix. You can also see that the eigenvectors are equivalent up to a transformation like if V is an eigenvector of a matrix. Performing such an operation will only change the basis of that matrix and will make K transposed V an eigenvector of the inner matrix if you want. This formula is well known actually in the literature, so this leads us to this equivalence. So basically we want to find the maximum T such that this matrix is SDP. And this can be done simply by computing the minimum eigenvalue of D prime. I'll give a bit more details soon. So basically the total projection cost in such case is 1 Cholesky, very fast in MATLAB, some back substitutions to solve a few systems, compute one minimum eigenvalue. We do need to compute this matrix, which puts at position IG the value Vi, Vg, very simple, and then we will need this kind of dot products to effectively implement and record the resulting constraint. And this is also very fast because we actually record a flat version of these matrices. We record it as an array, and same for this matrix, and this is a dot product, which makes this projection very fast if X is strictly SDP. Next, let me mention this property. The projection subproblem is quite simple in terms of computational cost if D belongs to the image of X, if they live more or less in some sense in the same space, because this means that each column of D and symmetrically each row can be written as a linear combination of the columns of X. We can equivalently say that the null space of X is included in the null space of D, such that if we have XD 0, this means capital D, lowercase d, is equal to 0 as well for any vector D. And in the associated paper, I show that the previous case, which is called case A, X is strictly SDP, belongs to this case, because of course if X is strictly SDP, this means it's invertible, it has n linearly independent columns, and its image will cover any D. So the quite interesting idea is that, if possible, projective cutting planes should adapt a bit its own evolution to seek this property. This is not yet implemented, but it's a nice feature to be taken into consideration. Let me go back to the first case A that I already discussed, and here I give a bit more details of what I said 2 slides ago. Again, the decomposition, but I named the property of congruence, which makes the problem equivalent to this one. So sorry to repeat some information, but I only want to make things a bit more clear. If we have to do this, if we calculate the minimum eigenvalue of D prime, actually the thought step length T star is this one. Why? Because it's enough to see that if we substitute this T star here and we compute the minimum eigenvalue of this matrix, the minimum eigenvalue of this matrix is 1 plus T times the minimum eigenvalue of D prime. Okay, so if I replace T with 1 minus 1 divided by the minimum eigenvalue of D prime, when I multiply it with the minimum eigenvalue of D prime, I obtain 1 minus 1. So this is the point where the minimum eigenvalue becomes 0. And if we go one epsilon step beyond this T star, you can do the calculation and you will see that the minimum eigenvalue of the resulting matrix associated to this slightly larger T will be negative. And there is a particular case if the minimum eigenvalue of D prime is positive or 0. Of course, in this case we can no longer apply the formula, because in such a case this means we have an open direction. We can go up to infinity and we remain SDP. Okay, so this is the easy case, and yet another quite easy case. is one where the property 1 is still satisfied. Property 1, what was that? D is in the image of X. But what happens if X has a rank lower than N, let's say C? So this means that X contain C independent rows or columns by symmetry, which are referred to as core. I will refer them as core rows. And the other dependent rows or columns are non-core positions. Now we use the LDL decomposition of X, and because this will enable us to find on the D will be a diagonal matrix actually in the LDL decomposition, and if we have some zeros on the diagonal, this will actually enable us to compute a kind of reduced Cholesky decomposition where matrix K and C is no longer full rank but has N rows and C columns, and we write X this way. This matrix has this size, and the image of this K and C is equal to the image of X, and if property 1 is still satisfied, we will be able to solve this in variables D', a bit like in case A. And the first intuition is to notice that we can project XD only over the core rows and columns, because everything on the non-core columns is dependent on the core columns. And then in the associated paper I provide more details for situation where this is more difficult, because D does not belong to the image of X, but this would make this talk too long. Even if the problem is interesting, I cannot cover everything. So what I can recall regarding the projection subproblem itself, if you want to take something home, is that it's very easy if X is strictly SDP, and more difficult if X is not strictly SDP. So we have the interest to focus and to change, if possible, the evolution of the projective cutting planes to work with many strictly interior matrices X, a bit like in interior point algorithms, where the generated matrices X are also strictly interior up to the last iterations, because projecting from an X that is on the frontier of the SDP curve can be more difficult. Let me just say here that instance below was solved by advanced only so strictly interior SDP matrices, because what do I have in this test? I chose a very small k, so that the outer approximation, the polytope, has only 11 variables, a quite big M. The matrices were here dense, with eigenvalues in the intervals provided here. This was my very first step, so I was happy, because Mosaic needed 7 seconds, the conic bundle needed 2 seconds and 23, and I did give it the optimal trace. And here we have in blue, we have only upper bounds of a standard cutting planes in blue. This is a fourth algorithm tested here, which means it needed a lot to prove the optimality here, because it has no mean to find that the outer solution is almost optimal. And here in red we have both lower and upper bounds of the new method, and you can see it's more easy to stop the algorithm, because the quality of the lower and upper bounds are very, very close here, and we can stop the algorithm with a precision, I think, of 5 significant digits. Then I performed the other test. Let's move on instances from the literature. Here we have a family of instances which is called Buck, which are derived from some vibration problems in physics. What happens for such an instance? I can solve it with my algorithm using the heuristic to find a starting solution, but I must confess I'm really very, very, very slow compared to Mosaic. here is the distance, here is the size of each instance. For instance, the last one, I have K1200. This is the value of n. We also have a number of given LP. The LP part has this number of constraints. And Mosaic is very, very fast for these sides, but essentially why? Because it is very sparse, and this enables it to simplify everything when computing and solving the Newton systems. But then I ask myself, what happens if I add some noise over all zeros of the input instance? And I added some quite simple noise, something like subtracting from each matrix, from each block, a matrix composed almost of only ones, and maybe with some 7 on the diagonal, because if I subtract a matrix that has only ones, this is a rank 1 matrix that can actually be expressed using an appropriate basis as a matrix that has only zeros everywhere and 1 in some diagonal position. And what happens with this way of densifying the instances? I can provide details on the paper. You see how the running time of Mosaic evolves as the size grows bigger and bigger. It's a whole different story, which is normal, because if you take the complexity of one iteration in Mosaic, it's not a linear complexity depending on the implementation and the optimization methods used behind. Here maybe it's cubic, I don't know exactly, but it's very, very natural. When n is so big, we need a lot of time. This is seconds. So basically here it needs more than 10 hours. It's normal. And see how the projective cutting planes running times gets higher. You see, for a very small instance, since the Newton systems are very easy to solve, you see its Mosaic is still 9 times faster, but this is my conjecture. If we use dense instances, and if n goes bigger than 1000 or at least bigger than this, it will be very difficult for an IPM to solve them. And you see, for instance, for this instance, the time needed by Mosaic is the time needed by projective cutting planes plus 142%. So I can beat Mosaic, and I did other tests comparing to other highly feasible dense instances. I needed to generate them myself, and they are provided on the website. Why? Because the most instances shared in the literature, if not all I'm aware of, they are sparse. Because it's easier to share sparse instances. The files are not very, very huge. But if I generate, as described in the paper that will accompany this talk, if I have, let's say, n 10 times k, because the algorithm I propose is better, is more effective when k is not very big. For this kind of instances, I compared to a few algorithms from the literature, and it works. It can be faster than Mosaic, of course. I don't claim I will ever be faster than Mosaic on any kind of instances, especially on sparse instances. My software is not yet configured. I'm one man working on it to deal with sparsity in such an effective manner compared to other software. But there are also other advantages. It's not only, I don't see this like a speed competition. It's not only a competition in time of speed. It's an optimization, SDP optimization method based of a polyhedral nature. It's different from other optimization methods. I think most software you see here is based on interior point methods, except the conic bundle. And I think Lorraine, it's specialized on low rank problems. Sorry if I don't remember completely, but the advantage of the problem of the algorithm I propose, this polyhedral nature makes it, for instance, an advantage more easily to adapt to change. Like if we solve a problem a very first time and then we extend the linear part. Why would we like to extend it? For instance, to follow a branch and bound decision. If we ever use this in a branch and bound framework, it will be more easily by a polyhedral algorithm to adapt to this kind of change. And I did some tests on a robust version of this problem. And of course, I will be faster than other methods. Why? What means robust? What will happen for the given program if the initial linear constraints are not actually explicitly written, but if they involve some robustness, naming that these are nominal constraints, and like in robust linear programming, we can imagine what happens to these constraints if we allow some robust rule to change the parameters, the coefficients, according to budget of robustness and things like that. In this case, actually, these nominal constraints will evolve into a set of prohibitively many linear constraints. So in this case, I can end up with this algorithm having to deal with two kinds of projections. I will have one projection in the SDP code and one projection with regards to the robust constraints, because the robust linear programming can be solved by cutting planes. So we can consider this is also one of the conclusions of my talk, and thanks for watching. Bye bye.